People need mobility because it gives people agency in the world. It allows them to be autonomous, to follow their own, to pursue their own goals, and in particular to engage socially, which is very important. But this is, and many of us simply take this for granted, but people with disabilities have substantial problems. And a significant number of people with disabilities are not even able to use a powered wheelchair. And this can be due to problems of communication, for example, being unable to use a joystick effectively, or if someone is blind, or if someone has cognitive limitations that make it impossible to follow a route to someplace. So for quite some time, people have been trying to build intelligent robotic wheelchairs. And these have a number of requirements. One is to be able to move safely and effectively in normal human environments. That involves having the kind of knowledge that allows one to make a plan, to know where one is and to make a plan to get to where one wants to be. And this also raises major issues of natural communication with the human driver. So I had a video made some years ago, which I want to share with you. We have a project to build an intelligent robotic wheelchair. One of the really important parts of this robotic wheelchair is to be able to move quickly, smoothly, and safely through an environment which may include dynamic obstacles such as pedestrians. The wheelchair is physically capable of traveling at up to 2.5 meters per second, which is faster than a brisk walk. We want to test that at these high speeds to make sure that it'll be safe even at extreme operating conditions. This work has been done by my graduate student and now postdoc, Jongjin Park.
I've been working on this problem with motion planning for mobile robots for the past few years. A lot of existing safe algorithms relied on slow-moving robots, so it's almost delegating the responsibility of avoiding the robot to people. One thing our algorithm does is it replans really fast, so it's replanning at the current setting 5 times a second. We can make it up to 10 or 20 times per second. The wheelchair can now run at its full speed, which is 2.5 meters per second. We can glide along an empty corridor really fast and safely. And it knows how to slow down at corners. It knows to slow down when there's an oncoming pedestrian. It can avoid people standing in the middle of hallway. It knows how to slow down when there's a person walking in front. It's figuring out what the current situation is, and it computes the probability of collision, cost of action, the current progress it's making toward getting to its goal, and it's optimizing everything in real time.
There we go. So as you can see, we've got this wheelchair and it moves safely and effectively. It's actually a whole lot of fun to ride. So let's think about what the wheelchair is actually doing. It's functioning as a partner for the human driver. The driver sets the goals. The driver decides how autonomy is shared. And it's important that the human can change their mind at any given time and change the nature of the autonomy, change the sharing of the autonomy, and allow the human to maintain control. The robot has a bunch of responsibilities. It learns a cognitive map of that environment from its own experience and uses the map to help the driver. And it can even learn social norms for appropriate behavior in particular settings. So here, this illustrates several levels. One of the things that we do is we use metrical mapping methods to build models of local regions where decision points, paths, destinations in the environment. And then we can represent that as a topological map which enables very fast and efficient travel. If a global metrical map is necessary, we can build that from there. A very important area in here is human-robot interaction and being able to interact in several different semantic levels of interaction. For example, the human might want to specify the goal, like take me to my office. Or the human might want to specify each decision, take the next left and then the second right. And these vary according to how much authority the human is delegating to the robot. And it's very important for that delegation decision to be easily changeable at any given instant. Now we have just a few minutes, and this goes into a little more detail on the model predictive control methods. So here we're showing at class change time in DAO, the robot is going through all of these, with all of these pedestrians. It is exploring hundreds of different possible trajectories. It's modeling the pedestrian behavior. It's using a method called model predictive control. Here's a point where it decides the only safe thing to do is not to move. And then it realizes now it's cleared out, movement is possible. So it provides very graceful and safe motion. We've also used this to allow the robot to learn social norms. It observes that people tend to stay towards their own right, and it incorporates that bias into its own planning. But what we were surprised to discover that when the robot visibly follows this norm and stays to the right, pedestrians around it follow the same norm more strongly than they did before. And so one problem that comes up is learning more norms and figuring out what it takes to live in human society. So among the research issues that this opens the way for are, what are the appropriate social norms? Who sets the standards? How does a robot demonstrate its trustworthiness to the people in the society? Because it's functioning as a member of society. Another key issue is autonomy. And people with disabilities are particularly sensitive about autonomy. Our position on this is that the autonomy belongs to the human. The human delegates that autonomy to the robot for particular purposes and can change that delegation at any moment. And there's a large set of questions about what the robot is able to learn, both about its static spatial environment and about the behavior of the humans around it. Thank you. I think we may have time for questions.
All right, great. Thank you, Ben, for the interesting talk. So now we are going to have the joint QA session. So we already have a couple of questions coming in, and you still can type questions in. So the first question is for Anhong. So this is about the VisLens. The question is, since the user is blind, how can the user ensure that the camera has captured or aimed at the whole interface?
There's an active area in HCI and accessibility called blind photography. So blind people take photos, and there are photographers that are blind. And there are a lot of techniques to help them aim. For example, there's some work from CMU Robotics Institute by Aaron Steinfeld on kind of automatically finding the salient object in the field of view to help blind people aim their camera. And in our technique, when the user take that initial photo, when we did the first iteration of the system, later on crowd workers can provide feedback to them. And also when they use the system to aim at the microwave, there's also ways that we can identify which area that the reference image is showing up in the field of view, and then give them corresponding feedback. And we like in the current version that we are trying to deploy, we also allow them to take a short video at the beginning and then use a combination of crowdsourcing and computer vision to identify the most likely frame that can work later on.
Great. So there's another question about this interface. So does every specific interface need to be labeled by the crowd, or is there the system able to work on classes of interface, such as vending machines or microwaves?
Yeah, that's a great question as well. So in our initial prototype, the first time the user encounter what that interface, they take a picture. But you can imagine the next time they come or somebody else use the same interface, it doesn't need to be labeled again. And also, as we are currently deploying the system, we are collecting more data, and also we are also looking into methods of crawling online web tutorials using images, text, and videos, such as in the dynamic touchscreen example. We are able to use these to build a more generalized model, and then use maybe the local one example to kind of fine-tune this existing model to work specifically for this. Yes, and actually there's another category of environmental sensing human AI systems that I didn't get a chance to talk about, where we collect data on the fly from online crowd workers, and we are training a local classifier in the background to gradually automate the crowd workers so the system can become faster and cheaper over time, that we can also aggregate multiple kind of sensor streams to train a more generalized model that can work in the future. Yeah.
Great, thank you, Anhong. So there's a question for Ben. Could the wheelchair ever go against what the human driver says? If the human driver tells the wheelchair to run into a wall, what would the wheelchair do?
Good question. At the moment, the wheelchair is programmed to avoid collisions. So it would not allow the driver to run it into the wall. But you could imagine situations where the human would have a reason that the wheelchair couldn't appreciate. There's good guidance for this from the way that guide dogs for the blind are trained. When crossing a busy street, the guide dog can put the person in the right place. And when the person says go forward, the guide dog can lead them forward, but the guide dog is also empowered to get in the way, to move in front of the blind person and push them back. For example, if there's a car that's coming through that path. So the guide dog can't say it's safe, but it can say it's unsafe and block the person's actions. And so I think that's an interesting direction for future work.
Okay, great. So I have another just quick question. So how far is it, maybe audience will be also wondering, to deploy this kind of wheelchair in the real world?
Well, that's
already being there.
Yeah, that's a very interesting question. What it really needs is clinical tests with people with disabilities. We've been using it as an AI platform, and generally with able-bodied and able-perceiving drivers. And so this is an opportunity for collaboration with people with disabilities and people who specialize in that work. And that, as you know, takes some time.
Great. Great. So we're running out of time. Thank you, Anhong, Ben, and everybody for this great session. And I'm going to pass back to Radha, who will introduce the next speakers.